Hi everybody, so here are the questions that were asked for homework 1C to do a video solution of, so here we go. Alright, so this was number 3, so it was 3, 5, 6, and 10. So number 3 says, while cycling at a speed of 10 meters per second, an Olympic cyclist starts going downhill with an acceleration of magnitude 1.2 meters per second squared. The descent takes 10 seconds. What is the final speed of the cyclist at the bottom of the hill? So let's kind of draw our cyclist here. Let's make a better hill than that. So let's do something like this. So the cyclist starts up here. Again, I'm using the dot model here, and then ends down here. So cycling at a speed of 10 meters per second. So this is the initial speed, is something like that. Then there's an acceleration. So I'm just going to say everything's happening in this direction. So everything's going down like this. So this is the initial speed. Then there's going to be an acceleration downward like this. And then the duration at which this happens for, so the time, is 10 seconds. And I'll write a VOVAT for this, where here's my initial moment, here's my final moment, and then I'm going to say my origin is right here. So we're trying to find out the final speed of the cyclist at the bottom of the hill. So we know that the cyclist is going to get faster, right? So the cyclist is going to go, let's make this actually just before hitting the bottom. So the cyclist is going to go faster. So there's the final velocity right there. So we know that in making my initial moment here, my final moment here. So we know the initial velocity is 10 meters per second. Final velocity, that's what we're looking for part A. The acceleration is 1.2 meters per second squared. And the time at which that happens is 10 seconds. So I need to find out an equation that can relate these three things. And that would be omega. So getting the final velocity, the initial velocity is 10 meters per second. The acceleration is 1.2. And then the 1.2 meters per second squared. And the time is 10 seconds. So plugging all that in, 1.2 times 10 is 12. Plus 10 is going to be 22. So the velocity is 22 meters per second. So that's part A. Then for part B, how far did the cyclist go in 10 seconds? Well, that's basically, I'm looking for now the displacement. So I just like to use this one, d equals v naught t plus 1/2 at squared, because I can then just plug in numbers and I don't really need to think too much about it. So the initial velocity is 10 meters per second, time is 10 seconds, 1/2 times 1.2 times the time, which is 10 seconds squared. So I know that this is going to be 100 plus, let's see, 1/2 times 1.2 is 0.6. So it's 0.6 times 100. I think that gets me to 60. So I think the displacement's going to be 160 meters. And there's part B. I'm going to double check that really quickly. Yep, that's right. All right. So so there's 3. Then in this one it says in 1998, David Cannonball Smith set a distance record for being shot out of a cannon, 56.64 meters. During a launch of the cannon's barrel, his speed increased from 0 to 80 kilometers per hour in 0.4 seconds. While he was being stopped by the catching net, his speed increased from, let's do this in a different color, 80 kilometers per hour to 0 with an average acceleration of 180 meters per second squared. So what's the acceleration being shot out of the cannon? And what is the time it takes for him to stop him? So I'm going to say this is part A, and I'll say this is B, just to kind of give it some. So we got some guy Get shot out of a cannon like you do. So, and the thing is that inside the cannon, so that's a cannon there, he starts maybe down here, and then he gets shot out with some velocity here. So this is going to be like, so the problem happens all down here. So like, here's his acceleration, that's his final velocity, where his initial velocity is 0. And then you also get, I don't think we need any of the other stuff, but you could even get, here's the displacement, right? All sorts of stuff that you can get out of there. So for part A here, I'm going to make a VOVAT. I'm calling my initial moment when he's sitting in the cannon, the final moment just before he gets out of the cannon. So his initial velocity is going to be 0. His final velocity, well, that's what I'm trying to look for. And then, oh no, it's his acceleration I'm trying to for. They told me the final velocity is 80 kilometers per hour. But that's not in meters per second, so I'm going to need to convert that. So I can go to my trusty friend Google, or you could convert this on your own, but you can basically say 80 kilometers per hour to meters per second. There you go. And we get 22.2 meters per second. So that's 22.2 meters per second. So just to let you know, there's in 1 kilometer there's 1,000 meters, and then in 1 hour there's 3,600 seconds. Or you could do there's 60 minutes in an hour and 60 seconds. You'll still get 3,600 seconds. So you can then do this conversion, you know, if you wanted to do it by hand. All right. So next up, I'm going to get my what else do I know? So I know the time that it happens for, which is 0.4 seconds. And I should be able to calculate the acceleration. So I could use v equals v naught plus at and then go from there. But I'm actually just going to cut to the chase and go with what the definition of an average velocity is. So it's the final velocity minus the initial velocity divided by the change in time. And the change in time is 0.4 seconds. Where my final velocity is this, and then my initial velocity is 0. So I can plug all that in. That's going to give me 22.2 meters per second minus 0, divided by 0.4 seconds minus 0. And I get my acceleration. It's just 22.2 divided by 0.4. So I can go here, 22.2 divided by 0.4, and I get 55.5. So 55.5 meters per second squared, which is quite a bit of acceleration to endure. So that's quite the feat. But then for part B, this is him going back from 80 kilometers per hour to 0, and then this is his acceleration, which is even worse. I mean, that's even greater of an acceleration than over there. So yeah, again, I'm gonna say here's the net that catches him. So here I'll draw him. There you go. There he is. So he gets in there, and then he's gonna get in the net. Right, the net's gonna probably give a little, and so there he is inside the net, right there. So he's coming in, right at some. So I'll say this is the initial moment. This is the final moment. So the final moment he's at rest, so his velocity is 0. But his initial moment, he's got some velocity, and it's 80 kilometers per hour. And then we also know his acceleration, but he's going to be slowing down, and when we watch that video, the acceleration points in the opposite direction of the velocity. So they're pointing in the opposite direction of each other when you get slowing down. So the acceleration points opposite the direction of the velocity when you get slowing down, but it points in the same direction when you get speeding up. So they're going to point in opposite directions. That basically means that I'm going to have let's say this direction is positive, this direction is negative. So my acceleration is going to be negative 180 meters per second squared. So I can then do a VOVAT. So my final velocity this time is 0. My initial velocity is, well, 22.2 meters per second, because that was the same 80 kilometers per hour as over here. And then we don't know the time. We're trying to find the time, right? What was the time? Yeah. But we do know his acceleration was negative 180 meters per second squared. And then I could use, I think again I'm going to use the definition of average velocity. Now I'll use V equals V naught plus AT. So I'm going to subtract both sides by V naught. So that cancels. And then I get, so I get now V minus, so this is all going over here, V minus V naught equals AT. Next up, I'm going to divide both sides by T. And I get V minus V naught over T is equal to my, oh, sorry, should have divided by A. So I should have divided by A because I'm solving for T. So that goes away. Now I get V minus V naught over A equals T, which is the final velocity is 0. The initial velocity is 22.2 meters per second squared. And the acceleration is negative 180. 22.2 meters per second. And then the acceleration is negative 180 meters per second squared. And now I get, well, I can just do this. So, well, the negative is going to cancel out, so I don't need to put that in. But 22.2 divided by 180. And I get 0.123. So 0.123 seconds. Yikes. It's a short time to accelerate. Wow. All right. So next up is number 6. You are driving in a car like you do. Determine the acceleration of the car in which the velocity changes from negative 10 meters per second to negative 20 meters per second in 4 seconds. So let's just go ahead and do this. So what's the acceleration? So again, I got a car that's going from negative 10. Let's do it this way. So I often think the negative direction is to the left, positive direction is to the right. So I got a car, it's moving to the left, like this. This is the initial velocity. And then it's going faster in the negative direction. So at the next moment, so here's my initial moment, here's my final moment. At the next moment, it's now going a little bit faster in that direction. Okay. So, and then I want to calculate the acceleration. This is all part A. So the acceleration is the change in velocity over the change in time. I'll say delta t, why not? So the acceleration then is going to be the final velocity is negative 20 meters per second. The initial velocity is negative 10, so it's minus negative 10. Divided by the change in time is 4 seconds. So I got negative 20 minus negative 10, that's plus 10. But I could even just plug it into my calculator and divide it by 4. So I got negative 20 minus negative 10, and then take that and divide it by, take my answer and divide it by 4. And I get negative 2.5. So my acceleration is negative 2.5 meters per second squared. Nailed it. Next up is determine the car's acceleration at the velocities goes from negative 20 to negative 18. So in this case now, and again I can draw a diagram to get a sense of what's going on. So again, I got an object here, object here. I'm still going to use the same convention that negative is to the left. So it's moving at negative 20 meters per second. So here's my initial velocity. And it actually gets shorter. So the final velocity is smaller, right? It's negative 18 meters per second as opposed to negative 20. And it does that in 2 seconds. So my change in time is 2 seconds. And then my final velocity is negative 18 meters per second. My initial velocity is negative 20 meters per second. So again, I could plug all this into Again, are we trying to find the acceleration? Yeah. So again, I'll say the acceleration is change in velocity over the change in time. And so in this case, this acceleration is going to be negative 18 meters per second. That's the final velocity minus the initial velocity, which is 20, divided by the change in time, which is 2 seconds. So the acceleration here, again, I'll plug all that in. So negative 18 minus negative 20, again, which is basically negative 18 plus 20. So I get that divided by 2, and I get 1. So it's a positive 1 meter per second squared. There we go. So that basically means, with this one, my acceleration was pointing in the same direction as my velocity. Right? With this one, acceleration is pointing in the positive direction, so that means it's pointing this way against the velocity, and that's why it's slowing down. That's why you go from 20 to 18. All right? And then part C says, explain why the sign of the acceleration is different in A and B. So, well, there you go. I just explained it. Because the acceleration is pointing in the same direction as the velocity here, so you get that speeding up, and it's negative. But then you get slowing down in the next one. So the velocity is pointing to the left and to the right here. And I calculated it, and I got it. It's to the right. So there you go. That's part C. So I'm not going to do part C. My part C was me just explaining that to you. All right. Lastly is going to be number 10 here. Is the rate of continental drift were to abruptly slow from 10 centimeters per year to 0.5 centimeters per year over the time interval of a year, what would be the average acceleration? So 1 centimeter per year, that's a speed, that's a velocity, right? As is 0.5 centimeters per year, that's another velocity. And the time interval is 1 year. So let's say I got some, continental drift moving at 1 centimeter per year, and then all of a sudden that same continent somehow misshapen, so it's, here we go, I'll just copy and paste it. Here we go. Now it's getting a little slower. Let's get it even slower. Let's do something like this. So now the velocity is 0.5 centimeters per year, right? And it does it for a year, so the duration of time is 1 year. And so, again, I'm going to use the definition of acceleration, change in velocity over the change in time. So that tells me then that the acceleration is going to be 0.5 centimeters per year minus 1 centimeter per year divided by 1 year. And I get, essentially this boils down to negative 0.5 centimeters per year squared. So the units work out that way, which that's an acceleration. It's measured in terms of distance divided by time squared, right? So it's the same idea if we got meters per second squared. It's just a different kind of unit. So there you go. There's your answer. And all right, hope that helped. Bye.